So in this segment, we're going to talk about monitors and the relation to conditional variables. We already looked at how conditional variables can be used for solving producer-consumer problems. Monitors are syntactic sugar on top of conditional variables, and they have specific, based on the type of monitor design, they have specific properties, and we really want to talk about the specifics of the semantics. Okay. So first of all, just to set up the contrast, what we're going to do is set up the contrastive semaphores. Then we're going to go back to the producer-consumer problem with a shared queue, and then look at how we're going to solve them with monitors. So if you had monitors, how would the program look, and what are the different semantics? Okay, so first of all, semaphores are great because they allow you to vend out a fixed amount of resources. Um, but they're confusing because they also have dual purposes because they have mutual exclusion and scheduling constraint kind of merged into one. So the mutual exclusion constraint is that at any given time the resource can be used by only one person, but there's also the constraint that the number of resources itself is finite. Okay, so essentially, if you look at conditional variables, they use locks for mutual exclusion and conditional variables for the scheduling constraint. So a monitor is essentially a lock and zero or more conditional variables for managing concurrent accesses to shared data. And the user monitor is really a programming paradigm. It's not an implementation. So conditional variables are the implementation. Monitors is how your program looks. And you need the lock itself to provide mutual exclusion to the shared data structure. They don't change that fundamentally. Okay. So the basic idea behind monitors is that one, they restrict the programming model, and at the same time, you permit access to shared data variables only within a critical section. The general program structure is one of you split into three sections. You have an entry section, you have a critical section, and then you have an exit section. Okay. So the entry section is you lock before you enter the critical section. You wait if the thing is already locked, waiting for some condition, and if you get signal on that condition, you wake back up, get into the critical section, and then exit. Okay. And normally what you would do with object-oriented programming is you would associate a lock with each shared object. Methods as shared objects would be critical sections, and you acquire and release the locks when entering or exiting the method that defines the critical section. In Java, all of these would be achieved with the synchronized keyword. Okay, so let's take a look at a simple monitor example with the queue and then study the different semantics. So similar to the producer-consumer problem with the shared buffer, we have a synchronized queue in this case. We have a lock, we have a queue. I'm going to go back and refresh the problem again just to help clarify things. So the add to queue method would acquire the lock and then enqueue an item into the queue, and the remove from the queue would remove it just dequeues. Okay. And what we're going to do is really look at the semantic difference between Mesa and Hoare monitors. Okay, so Mesa and Hoare, essentially, the difference between them boils down to what you expect from the signal and the wait functions. So how are they implemented? So if you look at the DQ example, first there would be a while which spins on if the queue is empty. So until the queue becomes empty, you keep checking, and you wait on the lock itself. So if the queue is empty, you wait on the lock. If there's nothing, you sleep. Okay, and not the main important thing to note here is that this is a while. So when you wake back up from the wait, so when you continue back again, you go back and check the condition again. Okay, so note that that's a while. And then once you break out of the while loop, you DQ. Okay, now let's look at another way of doing this. What if the while was an if? So when you wake back up, you know that you're already you could go ahead and get into the critical section. So you don't check the condition again. You simply progress and you get into the critical section. So the question is, what's the difference between these two? And semantically, what does that mean? What does it mean for the implementation? And the answer really depends on the type of scheduling. So we look at both of these, and they're used really for different purposes. The horse style monitors, which most textbooks talk about, is one where the signaler or the person notifying gives the lockup and the CPU to the person waiting. So when you're at this stage and you get a signal that comes in, you can just proceed because the signaler gives up the lock, and the CPU to the waiter, and the waiter kind of runs immediately. And then the waiter gives up the lock, processor back to the signaler, and when it exits the critical section, or it could wait again. The Mesa style one, which is what is most real operating systems do, which really has to do with the fact that it's easier to implement. The signaler keeps the lock and the processor. And the waiter is placed in the ready queue with no special priority, and you don't really know when you run after that whether the condition still holds or not. So in some ways, you have to kind of go back and check. So the Mesa style is the one with the while, uh, and the horror style is the one with the if. Okay, horror style is really nicer for proofs and um, studying the correctness of the problem itself because it's easier to reason about. And the Mesa style is more easier for implementation in a real system because it's a best effort. Notification does not mean absolutely that the other thread won't run.